Okay, I suppose we can start. And today I have a pleasure and honor to present our speaker, Professor Hietarinta, who will talk about integrable lattice equations. Jarmo, please.
Okay, thank you very much. I noticed some familiar faces in the list of participants. As I probably said already, I don't really bring something new that you wouldn't already know. Most of you would already know all this, but I want to point out some connections between various things. Okay, so let's start. I'll be looking at the KdV equation. First, it's important to realize that there are two kinds of KdV equations. The normal one here and the potential one, and they are related by this derivative. So this potential one is essential for some of the later developments, but the U here in the normal Korteweg-de Vries equation, this U is the standard form of bell-shaped solitons. So we have these in the potential KdV, these kind of solutions, regular and singular, and they translate into the normal KdV equation as 1 over cosine 1 over 6. And in this beginning part, I will follow very closely the paper of Wahlqvist and Estabrook, which I think is surprisingly before its age. It contains many relationships which we learned separately much later. So it's already 50 years old. So the main thing in this paper, or the founding, the basic thing here is that they derive the Backlund transformation. So one of the equations is like this. So W prime is the new solution, and W is the old solution, and the old and new are related by this. And then they consider several cases of this kind of relationship. U is again the one that contains the derivative. So we can have here a background solution and parameter K1, and then we construct a one-soliton solution with this parameter. But we could also start with the one-soliton solution and construct one two-soliton solutions with parameter K2 on top of this soliton with parameter K1. So they make a couple of steps, and then they finally were able to eliminate these derivatives and obtain this equation, which is a superposition principle, really. So we have a background solution and one soliton with parameter K1 and another soliton with parameter K2. And this is a formula that gives us the two-soliton solution. So this is important for us now. So one thing to note is that the superposition formula is for W and not for U. So we need the potential KdV equation. Related to this is that the asymptotic limit of U is 0, but for W it's non-zero. Okay, and then so we had this formula for superposition principle, but it's if you start to calculate, if you actually get your hands dirty and do the calculations, you will realize that to get the regular two-soliton solution, you have to have one singular solution and one regular solution. This was maybe a surprise, but that's what you find if you do the calculations by hand, by computer. Actually, then this is interesting. Wahlqvist and Estabrook went further and they constructed a three-soliton solution. So there's a little bit of misprint in the paper. But so here we have a two-soliton solution, 1, 2, and a two-soliton solution, 1, 3, and they have a common parameter, same one-soliton solution and two different ones. And if you use this, then this formula gives you a three-soliton solution. And would you believe it? They also constructed a four-soliton solution using like this. And all this in 50 years ago. Okay, so they did good work there. Okay, now comes this another step. Maybe some computer or AI system, you can teach them to construct backlund transformation by trying various things and so forth. But this step that now follows is something that you cannot really expect some artificial intelligence system to realize, because we changed the point of view. So this is again the same superposition principle, but now we interpret it differently. So I have already changed the notation that this is the 1, 2, this is a W2, and this is W1, this is W, this is W1, 2. So I added these indices to describe how we step from 0, 0, 0 to 0, 1, 1, 0, and so forth. So we can draw this diagram connecting that we can have the 1, 2 soliton here, and 2 soliton, and 1 soliton, and this is the background. Okay. Oops, what happened? Okay, so this one. Now we forget completely the meaning of this W. So these are just some numbers or functions or whatever for which we can do commutative algebra. So we write this equation as something that depends on these variables and some parameters. These are like the Ki and K3 and so forth. So let's consider these kind of equations. Q is some polynomial in its variables, but it has to satisfy certain conditions before we can make further use of it. And these are the conditions. So Q must be an irreducible polynomial. So it cannot factor because, yeah. And it's affine multilinear, meaning it's linear in all of these variables. And it must depend on all corner variables. So this is a condition Q. If we have such a Q, then we can put the equation of a Cartesian lattice and have dynamics there. By the way, I will change here the notation because this is very often used and it's sometimes more convenient. So we will use both conventions here. So it's some exercise in mind to change notation. Okay, so here is our lattice now. The variables W are located at these lattice points. And Q, we associate Q in these plaquettes because it connects the 4 corner variables. And then to have a dynamical system, we must also have initial values. This is one possible initial value. We have a staircase from far infinity, and then it goes like a staircase and to far infinity. So if we give values on all the red points, then from these red points, we can calculate this. Similarly here, this can calculate. And once these are calculated, we can calculate that and so forth. So we can fill the semi-plane once the staircase initial values are given. Another way is this. that we give the initial values on the square corner, or rather corner. And again here, once these are given, we can calculate that. Then we can calculate that. We can calculate from these, can calculate that. Then from these we can calculate that. So we can fill this one quadrant. So these are examples of initial values that give a well-defined evolution for us. There can be other as well. Okay, so we have a dynamical system on a 2D lattice for any Q that is multilinear and irreducible and so forth. So now we previously we derived one example of Q by the superposition principle of two solutions. But now that we have changed our point of view to the lattice, we can define dynamics with any polynomial Q which has these properties: irreducible, affine linearity, depends on four corners. And if we give suitable initial values, we can have good dynamics there. So this is a generalization from the KdV case. But now we have the problem: when is such a dynamical system integrable? Of course, the KdV superposition is integrable because it came from an integrable Backlund transformation of an integrable system. But now that we have generalized to Q, when would that be integrable? And I will show that the answer is actually construction of three-soliton solutions.
Sorry.
Both in a continuous and discrete. Is there a question?
Yes, just what definitions of integrability do you use here?
Well, actually, this is the definition of integrability. But I cannot say it as a definition of integrability. I would rather say that if something like this happens, then the equation which we get out has all the properties of integrability. But this is not maybe a definition of integrability.
Oh, okay.
Okay. So now because I refer to the three-soliton solution as a relationship to integrability, I will study first the continuous three-soliton systems, and therefore I have to go to this Hirota bilinear form. First of all, the definition here is that there's a Hirota's D operator, and it's defined like this. This F should be G. Oh, there's some notational problem. This should be small f, and this should be small g. And then the definition is like this, that there's a minus sign here in the middle. So it's like a Leibniz root except for the sign difference. So if we apply now, consider now the KdV equation in potential form like this, then let's define either W is minus dx log f, or if we go to the original KdV equation, we define U is to be dx squared or log f. And if we use this, then it turns out that the equation in terms of this capital F can be written in a Hirota bilinear form like that. This is just some computations. Now, again, let's generalize. We don't want to stick to the KdV, but let's see how general can we be. So let me take any P to be any polynomial, and then we'll see what follows for this kind of general case. Now, one property of this Hirota derivative is that there's a certain gauge invariance. If f and g are multiplied by the same exponential factor, which is linear in x, then they can be pulled through because d has a minus sign. So it can, this property is there. Okay, then we construct solutions to this equation. So it could be KdV or it could be something else. So we start with the one-soliton solution, which is either f is 1 or it could be a phase factor. And this will be a solution, the trivial solution, if this P doesn't contain any constant. And this, if you remember, for u, there's a second derivative of log f. This will kill the phase factor, but this will not kill the phase factor, but gives a constant. So for convenience, I will just take f is 1 here, and we can add the phase factor later if relevant. So one soliton solution is now f is 1 plus e to the eta. And the point is that this will work always because of this gauge invariance. So there's a linear term, that's okay. This zeroth order term, and then it's a linear term, which gives this kind of dispersion relation. Then there's a quadratic term, and it will be killed by this gauge invariance. So this is a one-soliton solution, and you will have the standard form. So that's okay. But now this is the interesting thing that in Hirota's method. Any equation of this particular form, P can be any polynomial, has two soliton solutions of this form, where the only condition here is that this, in addition to the dispersion relation, this sort of phase factor is given by this polynomial in a certain way. So any equation has two soliton solutions. This is similar generality as we can have on a lattice. We can have any kind of Q polynomial with some mild conditions. And it's kind of we can interpret this Q always as a kind of superposition to get the two soliton solution. So in Hirota's method also we can have easily two soliton solutions, and it's not related to integrability. So two soliton solutions, existence of two soliton solutions has nothing to do with integrability. Okay, so now we go to the three-soliton case. Maybe we get some conditions there, as Wahlqvist and Estabrook got. So the general requirement in the construction of several this kind of multi-soliton solutions is that they are line solitons in 1 + 1 dimension. And if one of the solitons, actually they are localized, if one of the solitons goes far away, but remains must be a standard two soliton solution. So if one approaches this problem perturbatively, one is led to this kind of formula where there's a combination of three solitons and the pairs, and then a triple term. But we don't know what the coefficient is. Okay. So next step is that we isolate this e to the eta 3 term. Normally, then, so we get this formula. Normally, when time goes to -infinity, this becomes large, and then this is the leading term. So it must be a two soliton solution. If time goes to plus infinity, then this disappears and we get this two-soliton solution. So the conclusion is that this one here should be a two-soliton solution. Therefore, it must look like a two-soliton solution. The beginning is clear, but then the remaining part should be what is usually the two-soliton solution part. There's a two-soliton coefficient and then the two exponential factors, plane wave factors. This is just from this principle that if one soliton goes away, the other should look like a regular two-soliton solution. So we must conclude from this combination, the blue one here must be the same as this one. So we have this, and then we get this is a two-soliton solution. So there's no freedom left, no freedom at all. We have already used all the freedom from P, the polynomial that defines the equation. We get the dispersion relation, it's fixed. And then we have this coefficient, it's also fixed. So this is either it solves the equation or it doesn't solve. Note also that this is completely symmetric. So it doesn't matter in which order we combine the solitons. Okay. So this is the indicator of integrability. If this three-soliton solution solves the original equation, then it is integrable by any definition of integrability. Turns out in practice. So, for example, I made this kind of search that I considered some general form of the P, not the fully general, but some generality. And I found that all the PDEs that I get were known integrable equations, except I got a couple of maybe only 2 or 3 new solutions. One is a combination of KP and David-Suerson with a few parameters, and another was a higher third-order evolution equation. Anyway, so this conditional three-soliton solution, it filters out all other equations except integrable ones in practice. So that's why I believe it's a good indicator of integrability. And let's go back to the Wahlqvist and Estre book. They also wrote the three-soliton solutions. But of course, you can combine many other ways. But Wahlqvist and Estre book observed that it doesn't, that the three-soliton solution you get from this is given like this. And it is totally symmetric and the permutation of these solitons. Okay, so this is the idea. So, and we saw that for the solitons in Hirota bilinear method, the same observation has been made, can be made. Of course, now that I continue from this, I will change from W to U and from this subscript till the head bar.
Isn't this exactly the 3D consistency property of discrete potential KdV equation?
Yeah, of course, and it will be in the next slide probably. Yes, here.
Yeah.
So now we go to the lattice version. And so in the lattice, we have several equations. This Q12 is the original, for example, KdV superposition principle. It depends on a background U, one soliton, another one soliton, and a two soliton. I have drawn it here in the bottom. So given these black dots, I can compute the red dot from this formula. And the same holds for each of the sides. If I give, this is maybe soliton 1 and this is soliton 3, I combine them, I get 1 three-soliton. Here is 2 three-soliton. So from this left-hand side. Now I have still 3 more sides to consider. This here contains tilde in each variable. So it is the middle one here. And from this, I should be able to calculate this triple shifted variable. Same here. This here is a common bar. So it comes from this solution, this equation. And so far, it doesn't matter what these polynomials are, I can always solve these. But now the condition here is that the triple soliton should be the same that we get here, only one kind of. And this is the consistency around the cube integrability condition. So this is also a very powerful condition, same as similar to the three-soliton condition. And we can now paraphrase the Wahlquist-Estabrook result that he has this KdV equation Q1, 2, and then they calculated the 1, 2, 3 and obtained this result, which is totally symmetric. And so they had this kind of formula already in 1973, but this is of course exactly the same formula we get now when we are only working in the lattice framework. So it's a nice observation that they already had this formula, this particular formula. Also, I noticed that I ask you to note that there are no U's without any kind of shifts. And this is a tetrahedron property, which has been quite important in the lattice development. So Adler, Popenko, and Souris used this consistency around the cube, and they made the assumption of tetrahedron property and some symmetry properties. And then they were able to classify the remaining equations completely, and they got this kind of list. And well, you can read this in the paper, but I don't want to go into details, except I want to note that Q4, which is somehow the biggest of the top equation, was actually first derived by Adler as a superposition rule for the Krzyżew-Novikov equation. This paper is rather short and a little bit difficult to read, but anyway, it's there. Yeah. So later I derived a simpler form for the Q4 because it only includes this Jacobi elliptic functions. So I didn't even write down the coefficients of this Weierstrass form. Okay. So this is the point. Main result here is that this result, this condition, the consistency around the cube condition is very important, and it allows the Adler's, Lopenko and Suris to classify equations with that property. But it's the same kind of property as the three-soliton constant. Namely, we can take the Wahlquist-Esterbrook thing and follow all these steps, and we get the same result. And for H1 is the KdV equation. So for this, Wahlquist and Esterbrook wrote the triple shifted result. Okay, so we have now generalized this starting from the KdV equation. We have been able to generalize it to other lattice, first to lattice, then particular these integrable lattice equation. And after the ABS classification, this side of integrability has really exploded. And I have really not much to say about that. But now let's start again from this KdV superposition principle or lattice equation. And now we go back to, I want to take a continuum limit of this equation. So, because from the equation we get a lattice, what happens if we take a continuum limit of the lattice equation? Should we get the same equation back? I think that would be nice to have. So this will, we have to now be careful to in doing this continuum limit. First, we have to connect the continuous space and lattice space. So we fix it so that the origin 0.0, is the same. And then we fix continuous variable x somewhere. And the discrete variable n is such that the x, the fixed continuous variable, is from the origin. You take n steps, and the step size is delta, then you reach x. Okay, so this is the connection. And now in a continuum limit, we make this step size smaller, and then we have to, of course, increase the number of steps because this x doesn't move. So we must have delta go to infinity, and delta goes to 0, and n goes to infinity, but so that x is fixed. So this is the way of approaching taking a continuum limit in general. Okay. Next, we point out that there are various ways to squeeze the lattice. One way is a so-called straight limit, which we take the square lattice and squeeze it maybe, for example, in the q direction, that is m, or n direction. But we just squeeze the square into a line. But there's another limit we call a skew limit. First, you take the square and rotate, and then you make these points approach each other like this. So this the result is a 3-point system, and from these, when these approach each other, it will produce a derivative. So there's this point here, and at this point we have a u and its derivative with respect to time. Okay, so this is, we consider this limit only. And in general, when we have a connection discrete and continuous, we have this discrete variable. And if n goes to infinity, then this kind of combination goes to a plane wave. So we must follow now the solitons of the lattice equation and make it so that we get the solitons of the continuous equation. Okay, let's see how that happens. First, we have to start with the discrete soliton solution, which we can derive using the Backlund transformation. It can be written in this form, that there's some rho factor, and this is actually the plane wave factor, the discrete form of it. And in this particular KdV case, we get this is as a solution. Here is the R. R is the soliton parameter, and these Q and P are the lattice parameters. And in the skew limit, this one, m minus n, will go to something, while the sum doesn't. So let's see. Here, notice that m minus n is this distance here, the old m and n, and the new m prime. Okay. So we write this in the form where there is an exponent m minus n. So we have to turn this upside down. It's done here. And then we write it, try to imitate this form like this. So now in order to have something like 1 over n from here, we see that we cannot do anything with this because R is a soliton parameter which doesn't go anywhere. So only thing is we make this go to 0 because it corresponds to this going to infinity. So we conclude that Q must be P plus delta, like that. Delta goes to 0, m prime goes to infinity, while m prime times delta, which we will be calling t, time variable, stays fixed. Okay, so we write the previous result in terms of replace the Q by this and only delta here. There's also delta here. So we can write it like now delta is solved from here. It's t over m prime. Now we have m prime here and m prime there. So we take the rest of it and we can take the limit and we get this. So this is a possible nice exponential factor like a soliton equations would have. That is some coefficient to t. So this is reasonable. So we have to take this kind of limit. Q is P plus delta. Okay. Now, let's return to the lattice equation. Now there's one more trouble here, that U is 0 is not the solution of this equation. Yet we want to make some limits here calculate. So U is not a good variable here. We should shift U by NP plus MQ. This is a solution you can calculate. So we have to change variables once more. So we define that U at n m prime shifted by nu or mu. It is some new variable v plus this extra piece. So that then the v can be 0 as a solution. Okay, now we have this term and this has delta here, so we can expand it. There's delta there, doesn't matter. So we substitute this to the above KdV equation, this part, and then we expand in delta. So if you do the calculation, you find that the leading term gives this result. This is a semi-continuous KdV equation, already known. So there's a time derivative, and then these are the two endpoints of the small piece of lattice, and this is the middle point. That's the derivative. So this is the first step of this continuum limit, and in the skew case, of course, you can do the similar calculations in the straight limit, but this is enough maybe here. Okay. Now we have to make one more continuum limit in this variable n. And also something must happen to this variable p. It turns out that one has to take p is 1 over epsilon and x is n times epsilon. And then this b will be written as t plus x plus mu epsilon. So this is maybe surprising that p is actually 1 over step size because epsilon is downstairs. So if we make this substitution here, then it becomes this. So now it's clear that we have to expand in epsilon, which is here, here, and here. Okay, and what happens? We get this expansion. I changed some signs here. Minus dtu is expansion on this side, epsilon squared ux, epsilon fourth, looks familiar, epsilon 6. This is something also something familiar. So we get the whole hierarchy when we expand in epsilon. Would you believe that? We started with KdV, we went to the lattice form, then we took the continuum limit, and we are back in KdV, but actually we have the whole hierarchy. Of course, we can now expand this t as t0 times epsilon squared plus t1 plus t2 and so forth, or 1, 3, 5, and so forth. So anyway, this is the
Jarmo,
yes.
it's not a hierarchy because equations with U5 is not a symmetry of the KdV. It's a correction. It's not a hierarchy.
What is this equation? Because
I mean equation at epsilon power 6.
yes,
it's not a symmetry of the KdV. Yeah, is it?
I think I have seen this equation.
Results on the lock screen. Check.
Oh, it is.
Yes, I think so. But the scaling, of course, is different here. Sorry about that. But I think this is a fifth order KdV.
No, cannot be. Should be the same sign at least. You have plus should be all terms. Something wrong here.
Maybe potential KdV hierarchy.
Yeah, maybe potential, but even for potential, the sign should be plus everywhere then.
I think I calculated this by computer, not this, but okay, this have to check it once more.
Okay.
But I believe this is a fifth order KdV, Lux KdV or something. But I'm sure there's in the audience expert who can tell also. This is okay. Okay. This has to be checked. Anyway, this is in a way we have now made a round trip here, like this. We started with partial differential equation, KdV equation in the potential form. Then we took a Backlund Alquist and Estabrook used Backlund transformation to construct the superposition rule. Then we reinterpreted this superposition rule as a quad equation on a Cartesian lattice. Then we generalized to any kind of quad equation with this consistency around the cube as indicator integrability. And once we are there, then the classification means that explosion of research in this level. Okay. Another point was here that this round trip start with KdV, get superposition rule, get lattice equation, take a continuum limit, you go back to KdV. So I think this is very satisfactory that they are all related. So, okay, so now I'm closing more or less some talks. What about this integrability then? So in Hirota's approach, it's clear, very clear, and the founding property that the existence of a three-soliton solution is same as integrability, fundamentally. But two-soliton solution is nothing. Anything, any equation can have two-soliton solutions if it's in a Hirota form. In lattice quad equation, we have the same thing. You can define any kind of Q to define a lattice evolution, but only those that have the consistency around the cube have any chance of being integrable. I might add that consistency around the cube is a little bit weak in the form because if you have several different equations of the sides of the cube, then you can have a consistency without integrability. So I think in this case, the existence of a good Backlund transformation is the more strong requirement. But anyway, here I would like to point out that both approaches lead to the idea that the order in which the three solitons are combined does not matter. So this is somehow at the meta level what happens in this. But what's more, in the Yang-Baxter equation, it's like the same thing. Everybody has been drawing these three lines, and they tell that you can have scattering, first 1, 2, then 1, 3, then 2, 3, or you can have first 2, 3, then 1, 3, then 1, 2 scattering, and the result is the same. That's a statement of the Yang-Baxter equation. Of course, Yang-Baxter equation addresses completely different situation, but I think maybe in the Yang-Baxter maps, they also related to this. So this is somehow, in my opinion, the basic somehow underlying of what, how can I say, meta level point of these 1+1 dimensional systems, integrable systems. Now there's then, of course, what happens in the 2+1 dimensions. What are the corresponding things? I leave that as an open question because I don't know what to say. But this is one more practical thing which you can maybe mention to your students. Note that I used several different functions here. U was the one that gave us solitons, actual solitons. W was the one that we used for lattice and the superposition formula for lattice equations. F was the one that we used to construct these three-soliton solutions in the Hirota formalism. And V was the one that we used to get the continuum. They are all related in reversible form to some degree. So, but my final comment, it's important to choose the correct form that is suitable for the problem, because the superposition principle, if you try to write it in terms of U or F, I don't think it looks so well. Maybe you cannot write it in terms of that. So you have to be free to change to the variable that is suitable for the particular problem that you're dealing with. Okay, so that's probably all I have to say. Thank you.
Thank you very much. Are there any questions, suggestions, comments, please? Yes.
Well, I have a comment. So I do agree actually that the 3D consistency or consistency around the cube is the strongest integrability criterion. You just automatically you get Becklin transformation, etc. But in most of the integrable discretizations of 1+1 equations, they are integrable in the sense that they have lattice pair, which are the Darboux transformations of the lattice pair of the continuous case. They are integrable in this sense, but they don't have the consistency around the cube property. So actually, for these cases, you don't need even consistency around the cube, because you can actually again calculate similarity transformations, like we can call it again Darboux transformations, and you get automatically a Becklin, and you can construct soliton solutions. I'm not sure about three-soliton, to be honest, but 1 and 2 solitons in more examples I checked, you actually receive, you obtain, and actually I used 2 examples is the NLS equation that you got, the discretization is the Adler-Yamilov system, and then the Hirota KdV that you get something also this you can also the Hirota KdV also doesn't have the consistency around the cube property, but you can still construct a Becklin transformation systematically using the lattice pair.
Yeah, it's true that Hirota's form of KdV doesn't have this form. Yes, of course, this what I have described does not contain all integrable systems. Certainly not. But of course, once you have consistency around the cube, you can easily construct a lattice pair, so it goes to that direction. And Becklin transformation also from the consistency cube itself.
And a small question, actually, I use this for the Adler-Yamilov system to get back the NLS equation. I pretty much copied your continuous limit that you use in your book as well. Actually, I have it right here. It's quite popular here book. So. And it worked. So the question is if it works in most cases, the same limit, or is there a recipe or how to find the continuous limit in other cases?
I don't have a general solution. Maybe if Frank is still listening, maybe I have to ask him.
Well, yeah, I can comment on this. Actually, I computed also the continuum limit a long time ago of the Q4 actually to Adler-Yamilov, and it works in the same way. But you have to be a bit careful with how you deal with the small parameter, because it enters through elliptic functions. So that's a subtlety that occurs. If you go to higher rank systems like Boussinesque, then again you have to adapt a little bit the skew limit issue. But then it becomes a bit of a technical discussion really how that works through. So my feeling is that it works always.
Okay, other questions?
Hello, Jarmo.
Yes.
So when you search the three-soliton condition, we insert the KdV type binary equations using the three-soliton equation, three-soliton condition. Did you find any four-dimensional equations? Really four-dimensional?
Not really four-dimensional. There is this fake four-dimensional, something like dx, dy, dt, dz.
Mm-hmm.
But it is, it factorizes, so it's not the interesting case.
Mm.
No, of course, we have the 2+1 dimension, but nothing in higher dimensions passes three-soliton test. In this derivation, I used arbitrary dimensions because two-soliton solutions, they can have arbitrary degree and arbitrary number of variables. So
Okay. And one more question is, your KdV type equation is the equation with constant coefficients, not variable coefficients.
That's right. This was an assumption. Yes.
Mm-hmm. Okay. Thank you.
Me too. I have a question. Is the soliton nature of such discrete systems could be expressed algebraically? I mean, a construction similar to the Sata-Grassmannian and vertex operators which represent the soliton solution, for example, in KdV and Kp type hierarchies. So my question: could this soliton structure be interpreted in terms of vertex operators?
Sorry, I'm not very familiar with this, so I cannot really say. No, sorry, this is not familiar approach to me.
Jarmo, what about self-duality equation? Does it fit in your scheme? It seems to be four-dimensional and integrable.
Which one?
The self-duality in Young-Mills theory.
Ah, yes. Well, interesting question, because it can be 2+2 dimensional easily. Yeah, I don't know. This Young-Mills, there are many statements about Young-Mills equations about the integrability, but most of them are somehow I'm not comfortable with those statements.
No, at least there are exact, you can construct three instanton solutions with full number of parameters. It's analog of your three-soliton solutions, isn't it?
Yeah, that would be, and then, yeah. Yeah. Okay, and that would be in how many dimensions? 2+2?
Yes, 2+2.
Okay, that's interesting, because in yeah, because can you then make a reduction to 2+1 in such a reduction that it goes to one of our familiar 2+1 dimensional equations?
There is a reduction to 2+1 integrable equations. I think it was studied by Zakharov and Monakov probably long ago. There is a reduction, yeah.
Okay, that sounds interesting, yeah.
And my comment about this expansion, usually when you have this continuous expansion, it looks like a hierarchy of symmetries, but it is not usually. Usually you have, equation plus some corrections, etc., and they are not member of hierarchy. Definitely equations that you write in, in your slide is not a symmetry of KdV. I mean, the term is at epsilon 6. Did you check that they commute?
No, I did.
It is not a symmetry, it's just a correction.
Yeah, I have nothing to add except that they look like known high-order KdV soliton equations. That's all I can say.
But the coefficients are different.
Of course, you can
No,
scale.
no, sorry, I remember it's Frank, they have the results this long time ago, and they prove the continuous limit of that equation, that discrete KdV equation, finally gave the whole hierarchy of the KdV. They found the recursion operator.
Maybe in France it is okay, but what we have seen here is definitely not a symmetry.
Mm-hmm.
Absolutely, definitely, because first of all, signs different, and secondly, coefficients are different. No, it's not.
Well, and maybe it was just a computational error that slipped in. I don't know. This refers probably back to work by Capel and Wiersma in the 1980s.
Yes, yes, that's what I meant. Yes.
Yeah.
Yes.
Well, this has to be checked. The details and the numbers and signs have to be checked.
Mm-hmm. I just one more comment about the self-dual Young-Mills equation. If you look at the Cauchy matrix structure, and you can see the equation will be related to either KP, the matrix KP hierarchy, or the matrix AKNS hierarchy. It's four-dimensional.
Yes, and I wonder how these higher dimensional things fit into, because we, of course, we have a high dimensional version of Young-Baxter that should be somehow related then to higher dimensional soliton equations. If we took now the 1 plus 1 dimensional root, and if we start with 2 plus 1 and continue, what do we get? Open question.
And I also remember that David Cow long ago studied n-wave equations, and basically there was no restrictions on dimensions in his consideration. That, if I remember correctly, but was so long ago. Yeah, at least he can study 3 plus 1 dimensional n-wave equations.
Okay. Let's thank the speaker again. Thank you very much.
Thank you.
Thank you very much.
Interesting questions, and see you next time.
Thank you, Jarmo.
Bye.
Hello.